Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. And today I'm hosting Manuel Dahnert, and we will be talking about his paper, Panoptic 3D Scene Reconstruction from a Single RGB Image. This paper was accepted at NeurIPS 2021. Hello, Manuel, and welcome to the podcast.
Hi, everyone, and thanks, Itchik, for having me.
Manuel, can you introduce yourself?
Hi, I'm Manuel. I'm a PhD student in Germany at the Technical University of Munich. And there I'm a PhD student in the group of Matthias Niessner.
And who are the co-authors of this paper?
So this paper is joint work with Ji Hao, who is also a PhD student, just recently graduated from our lab, and Matthias Niessner, and also Angela Dai, who is also a group leader or assistant professor at the Technical University.
Now, tell us, in like a TLDR format, 2-3 sentences, what is this paper about?
All right. As the title says, it's about 3D scene reconstruction from a single RGB image. So as input, we take a single image of an indoor scene, like your room, for example. And the goal is that we reconstruct everything inside the camera view, basically, and try to get a 3D model out of that. And together, we also perform the Panoptic reconstruction task, which is both reconstructing what is occluded, but also like higher level ideas of semantics and instances.
Okay, so you basically touched on what the problem that this paper is addressing, right? Is the panoptics. But can you now we're moving on to the introduction section. So can you elaborate a little bit about what is the problem here?
For us, we are tackling the indoor reconstruction. It's a bit different from outdoor reconstruction. So from a given RGB image, we try to reconstruct everything which was occluded. So from the single image, you won't capture everything. And here we try to basically hallucinate or plausibly reconstruct everything which was occluded, given the input image. And that should be as high quality as possible. And the panoptic here means, maybe that we're going to touch on that a bit later, but that means that we're going to perform two tasks together, actually, to get more semantic information from the 3D information.
So really, that's the major challenge, right? You have only RGB, right? And you were trying to find a lot of information that's not there, right? You want to find the geometry, you want to find semantic segmentation, you want to find instance segmentation. All of this information is not there. And you're still trying to do that in 3D. That's super challenging. Exactly. So why is this problem important? Like, where can you use that?
You can think of many applications. So, for example, currently we also have our live streams, which you don't hear in the audio or don't see in the audio. But here you have a static camera, which doesn't move. It's still a video stream, but still it doesn't move. And if you only take a single image of that, would be one application. So for every, conferencing system, it might be really interesting to also reconstruct like the conference room, which the people are then being sitting inside, or also for robotics, actually, when you have a robot and you get like an initial image of the scene and you want to do planning afterwards. So you don't have a trajectory of the robotic vehicle moving. You can do like some initial planning from a single image, for example. But also, mixed reality, augmented reality, where you have your phone and you take a picture of your room and just want to reconstruct it. Like for when you want to place furniture or something like that.
That's super interesting, right? All of these cool new applications. After COVID, we're all sitting at home watching monitors, right? We're using cameras. Maybe there's a better way to use those cameras to actually immerse ourselves in this kind of a 3D environment. That's super interesting and challenging. Before we dive into the approach, let's talk about some important related work that your novice listeners needs to read before reading this paper.
So one really basic paper which we build up on is the idea of the panoptic task. The first word in the title, panoptic, means that we're going to combine semantic segmentation and instance segmentation. And that's building up on the idea from the paper's panoptic segmentation, which proposed this task in 2D. And we are basically lifting this task from 2D to 3D. So here, panoptic means basically doing semantic segmentation, so getting the semantic class of each individual object, but also segmenting out the individual objects. So basically, when you have multiple chairs, that you know, okay, that's chair number 1, number 2, number 3, and so on. Another really interesting and cool paper, which was basically groundbreaking was Mesh RCNN. So maybe some of you know Mask RCNN, which builds up on top of like RCNN and this entire recognition pipeline. And Mesh RCNN extends Mask RCNN by also reconstructing the 3D objects from the 2D detection. So for every detection you get from the image, you will also try to reconstruct the 3D object. And yeah, because you already have it, you know the instances, so you know the instance segmentation, and you also get the semantic information. And a third one, which would be total 3D understanding. So that's a really cool paper as well. It tackles a similar approach or a similar task, so single image reconstruction. But the interesting idea behind that paper is actually that they decouple scene and objects. So basically the scene layout, basically the room box which you're sitting in, versus the individual objects which are seen in the image. And with that, you can have like a nice decoupling of the scene complexity.
Very interesting papers. I'm going to put links to those in the episode description. So now let's dive into the method. How do you do it?
That's the fun part. We start with the single RGB image. So we have an image of an indoor scene, like a room, as I said. And then we have a 2D convolutional neural network. So yeah, we have a depth prior. So we first try to estimate the depth. So there are quite some approaches doing depth estimation from a single image. And we combine it together with actually Mask RCNN. So we also have an initial 2D instance segmentation of that image.
Is
like
this
2D features.
Supervised?
So the entire approach is supervised learning. That's a good point.
That means that you have for the depth, you have the corresponding depth map with the RGB input, and you have the detection for the RCNN part of the pipeline.
Exactly. So we all have this information because we're working on top of 3D data in the background. Data was like an important part in this project to get clean and good data and consistent data, which is not that easy in the domain of 3D. And quickly finish the method approach. So we now have like all our 2D information. We have depth and we have features basically, and also instances. And with the depth information, with our depth prior, which we learn, we lift it, basically we back project it into 3D. And with the depth, you can just put the pixels where they belong in 3D. And that's going to be together with the instances and also the features. So we try to basically lift as much information from 2D to 3D. And then in 3D, that's actually a quite interesting approach. So we have a sparse voxel grid. So each point which we back project to 3D is going to be a sparse voxel. And a voxel is, like a pixel in 3D. And previously, many approaches were dense. So we had like a dense voxel grid. But there you're quite limited in the resolution because for every increase in resolution, you grow cubically. But if you think of it like you have a lot of free space, so everything until you first see the first object is actually free space. So there's no real information for these voxels. So you can basically ignore all of these. And here you can use sparse voxels, which is a quite nice representation, which saves you a lot of memory. So that was quite important. So we can, first of all, have bit higher resolution, and everything still fits on the GPU, so we can still do our nice trainings.
Okay, so let me just recap to see that I understand everything, okay? You get RGB images input. You feed that into your 2D backbone. You get depths and segmentations. Now you take those and you lift them up, right, into this voxel grid. Right. So now you have, and the voxel grid is not dense. It's a sparse voxel grid because most of the space is empty. And then for every voxel, you have depth, features, and instance information.
Exactly.
Okay. And then what?
So then we are now in the 3D space and we have sparse or hybrid 3D unit. So what hybrid means here is, okay, we first encode the sparse information, but in the middle part or in the bottleneck part of the unit, so we have a unit architecture, we have a dense part because it's quite tricky to do completion on sparse data structures. So in the middle, where we can have like a higher or lower resolution, we still can have like a dense voxel grid. So we first have our sparse voxel grid. go down a few layers, a bit of the resolution. And then in the middle part, we have a dense part where we do then the completion. And the decoder part of our unit, you can think of refinement. So in the middle part, from like the output of the dense part, is already like this blobby reconstruction, but completed. And at every level of the decoder, we try to refine it. And there we again need like this sparse data structure, because then we're going into high resolution when we decode everything again. And then we have like the sparse output at the end again. And
so this is like kind of a coarse to fine approach.
Exactly. And speaking of outputs, so we're going to have 3 outputs for the Panoptic task. So we have the geometry, so we can work with the 3D. This is encoded as this distance field. So it's not only binary, occupied or not, but we have like distances, so we can extract things via marching cubes and get like some quite nice details. Then we have the semantic information. So here every voxel carries the information of the semantic class, and then also an instance ID. So which object this voxel belongs to.
Okay. So I'm going to recap from the beginning again, just to see that I get it right. Okay. So you have the RGB image. You fit that into your 2D backbone. You get the depth and you get your segmentations. You then lift that up into 3D sparse voxel grid. You take that voxel grid, you go from this kind of a coarse to fine approach, and then your final output is this signed distance field that you can reconstruct the surface from with a semantic segmentation and instance level segmentation.
Exactly.
Okay, so we got the pipeline covered. That's what it does end to end. Very impressive. Very, like, you're doing a bunch of things all at once. Like, this is kind of a holistic approach, which is really interesting, right? Because computer vision or 3D vision or the field in general always kind of breaks them down from each other, right? You either do semantic segmentation or you do surface reconstruction. And I think one of the cool things about this paper is you're doing it all at once, which is, well, I always try to think how our minds work, right? We don't do those things in our head. It just all happens at the same time. So that looks like definitely a good way to go.
And I think that's also currently like where the field is going a bit, so that we go a bit away from these individual tasks and try to have like higher level task or understanding. So action recognition or these panoptic reconstruction idea. So I think the field is going more towards higher level or multitask projects.
Yeah, and it makes sense because they have like complementary information levels between them. So it makes sense to go to a holistic one, because otherwise you're missing some information that you're just not using for no good reason. Okay, but we digress. Can you tell us a little bit about the data? Because that was a very important part of your approach.
Yeah, that's a good question. So train both on synthetic and on real data. Because it's a new task, we had the control of our data. And synthetic data is quite a nice playground for that. And for that, we used the dataset 3D Front, which is a nice 3D indoor dataset. I think it was published 2 years ago or so. And we were quite happy that it's out there. Yeah, it has like 3D scenes of apartments. And we used also Blender Proc, which is a nice repository to render high resolution images or high quality images. And we could also parse like all the 3D information from that and get like the ground truth data for that. And on the real side, we used Metaport, which is a real data set. So images of real data and also the reconstructions of real data. And the difference between cleaning up real data and working with synthetic data is quite big. So working with real data, you have like many pitfalls and you really have to carefully check all your data that there are no invalid scenes or invalid frames. And you basically have to work with the limited amount of data which is there. And that was a nice observation as a PhD student, basically to see, okay, how is it to work with synthetic data or real data, and how do you go from one to the other?
Yeah, the gap between synthetic is really so huge, especially in the 3D domain.
So many people think of this gap actually like on the pixel level, which is quite interesting. So they see a synthetic image and they see a real image and they think, okay, that's not the same. So there's a gap. But to my understanding now from that paper actually, or from that project, is not the pixel level, but more of the complexity. So what's the content of the scene? So for synthetic images, you often have like really simplified structures. You have one bed in the background and one cabinet. But for real data, you have like clutter on the table, bottles lying around, clothes hanging over the chairs. And that's just totally different kind of domain gap in a sense. And that was also one difficult aspect of the project.
Yeah, even just the wrinkles on the bed, right? That like a dead giveaway. Moving on to the results section. So this is like a new task that you're introducing. So how are you even evaluating this? What are the experiments that you've done?
So what you can do to evaluate the approach is, okay, we just do a feed-forward approach or pass-through. So we take a test image, pass it through our network, and because it's supervised, or we have the ground truth for everything, we evaluate it like the predictions of the network with the ground truth. And for that, we are going from the Panoptic segmentation paper, we adopt their metric and also lift it to 3D. It's a bit complicated. There are two parts, but basically what you try to estimate is everything. So the metric which we're going to use is like this Panoptic reconstruction quality metric, which is adopted from the 2D idea, that we try to measure the quality of the reconstruction, the semantic reconstruction, and also the instance reconstruction or instance segmentation. And one key element here is that you can think of your result of being colored. So when you look at the paper, you see a lot of colors in the visual results. And every color denotes like a different instance. And then you can check with all your predicted instances in 3D to check what's the overlap with the ground truth instance. So you do basically a matching to see if your object is overlapping with the ground truth object. As a second step, you check if the semantic class is the same. So basically, is this object, which is overlapping the other object in ground truth, are both, for example, a chair. And the overlap is defined by the intersection over union metric.
So the intersection in the voxel domain versus the union in the voxel domain.
Exactly. And with that, you get like a percentage or ratio. With that, you can have a threshold and say, okay, these are overlapping, yes or no. And then you do the follow-up checks.
Okay, so you have the bold numbers, right? So you evaluated it, you set some baselines. So because this is a new task, so what did you use as baselines?
There's this entire branch of literature from semantic scene completion. So they also go from a single image, but often they actually also have the depth information. So they already have like some advantage, these approaches. And how we evaluated some of these approaches is actually, okay, we train them with the predicted depth, which we also used. So they cannot use the perfect depth, which they would usually get, but they still have to work with the same depth information, which we use, and try to reconstruct the semantic information. So they don't do instances. To get the instances on top of these approaches, we use the clustering approach. For every voxel, basically, you check the neighboring and try to cluster semantic regions into instances. And with that, we also got the full Panoptic output for these semantic scene completion baselines. Then we also, as I said in the beginning, we compared with Mesh RCNN as like this groundbreaking idea of going from 2D detection to 3D. One caveat about Mesh RCNN is that it does not reconstruct the structural elements, so the walls or the floors of your image, because it doesn't detect them basically as objects. So what we get from Mesh RCNN is only the objects, but we can evaluate them separately. And then finally, we also compared with Total 3D Understanding, which gets as output also reconstruction of individual objects. And this, rather coarse room layout, basically a box, a 3D box of how the method thinks your room or your camera is rotated to your room. And with this box, basically, we can extract, okay, the floor plane, so the bottom part of the box, and the side parts would be the walls. And with that, we actually also get like the full output.
In which cases does your method fail?
On synthetic data, you can see that we get quite impressive results visually and also in terms of the numbers. If you scroll down to the real results, you can see that there is quite a big difference. So honestly, there's still a lot of room for improvements on the real data.
Why is it failing there? Like, is it a data problem? There's not enough training data? Is it the noise? Is it the occlusions? What do you think is the problem with the real data that makes the method fail there?
First of all, it was also the limited data that we had in the real domain. So here we saw quite some overfitting, and with that on the training data, you cannot do too much. That's also because we had to do a lot of filtering in the 3D data. So we didn't end up with too many frames or pairs of 2D and 3D pairs that we could train on. Then also the scene complexity, what I mentioned before. So the 3D front data set is really nice, but it's kind of simplified in the scene complexity. So as I said, we have like individual objects, but no clutter. And if you look on the real images, you have like a lot of clutter, and there also your 2D detection already fails or is not perfect, basically. Because you would, first of all, define what's an instance. If you have like a table full of clutter, do you want to define everything as an individual object, or do you want to treat a single table with clutter on top of as individual object? So the scene complexity, I would say, is an issue. And since we took a heavy depth prior in the approach, so we estimated the depth, that's not that good on real data as it was on synthetic data, also because of the limited training data amount.
Do you have any results that surprised you? Anything unexpected? Anything that you thought would work one way, but actually did something completely different?
Consistency in the data was a really big thing. It surprised me that when I had like a bug in my data, that it was not able to reconstruct like basic elements like the floor. So usually the floor is like rather easy to reconstruct, like it's a big plane basically. And because I had one bug basically in my data generation, even that simple geometry was not able to be reconstructed. So that was quite surprising once I ran the first experiment on the data, but then had to go back and figure out and debug correctly. And after the fix, actually, it was quite able to reconstruct, at least like for the real data, these simple objects or geometry parts.
Okay, conclusions and future work. How do you see the impact of the paper going forward?
So, I mean, I hope that people will build up on top of it, because actually, as I said, that there's quite a lot of room for improvement, especially on the real data, I would say. Then also we had some constraints on the view selection. So what I really would love to see in the future is like basically in the wild application of. So really just going somewhere, take a single image of a room, and it works perfectly on real data. And that would be super cool. So basically you take a photo, you have your phone, and afterwards you get like this 3D mesh on your phone with semantic and instance information, and you can scroll around, rotate it, and maybe use it in some of the applications.
Yeah, really cool. I can definitely see something like that being incorporated in some cool app, maybe for architectural design or something like that. Now to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments that you had in the review process, maybe even the ranks that it got and things that you ended up incorporating into the paper that made the paper better.
We were actually quite a bit nervous when we submitted, because first of all, NeurIPS is maybe not the go-to computer vision conference. I mean, it's top tier, but we're a bit nervous because it might be not the perfect fit for such a application-oriented computer vision approach. And also we were quite a bit nervous because of the results on Matterport, so the real data, because they were not quite as impressive as what we would have hoped. Interestingly, in the review process, the reviewers were quite happy with the task, so that we were trying to tackle this holistic direction and we're proposing a new task. Definitely what you said regarding the evaluation, like it's a new task, how do you going to evaluate it? So there's always not the perfect metric to especially evaluate such a complex task. So there is definitely some discussion what's like the correct measurement and how do you evaluate something complex as panoptic reconstruction. But definitely there was always like, there is this baseline X, maybe you can also compare it to that. I mean, there's so much work similar to that. We hope that we selected like a broad set of relevant baselines across the field, from single images, single objects, to semantic scene completion, to this total 3D understanding.
Yeah, I can totally imagine how this kind of paper you'd be nervous about, because all of these kind of new field, new problem papers, it's a huge risk. Like, it's a high risk, high reward kind of problem, right? You suggest something completely new, and you're taking the risk of someone just saying, well, you didn't compare to the right baselines. Well, there aren't any baselines. It's a new problem. Okay, Manu, thank you very much for agreeing to be a guest on my podcast. It's been a delight to have you. Until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.